So this video is going to be on the second lesson of the second chapter of geometry, and it's going to be on statements and conditionals and kind of the basis of how we're going to talk about stuff later on in the unit. This is going to be kind of a long one, so you might want to take this in two parts or two settings or whatever you have because there's going to be a lot of information in this lesson. So we're just going to try to take as best we can. So first off, some definitions. So a statement is simply something that can either be true or false. So if it has the possibility of being either true or false, we can call it a statement. And the truth value is simply what the grade of the statement is. Is it true or is it false? That's the truth value. If it's true, then the truth value is true. If it's false, then the truth value is false. That's just how it goes. And then the negation is the opposite of a statement. And the way we talk about opposites is that it holds the opposite truth value. So the opposite of a statement has to be the opposite truth value. So if the statement is true, the negation would have to be the false version of that statement. So for example, if you say, when it is snowing, it is cold outside. Well, that is true, right? If it's snow, or sorry, when it is snowing, it's cold outside. If it's snowing, then it has to be cold outside. There's no other way for it to be snowing. You can't be snowing and be hot outside, otherwise the conditions for snowing would not be met. So that's a statement with a truth value of true. The negation would be when it's snowing, it is not cold outside, and that would have a truth value of false because if it's snowing, it has to be cold outside. There's no other way for it to be snowing unless for it to be cold outside. And notice here that we use the phrase not. So a negation usually includes the word not in it. I guess there are some ways you can do it without using that word not directly, but it usually has to have some form of not in it in order to be a negation. But that's all it is it takes the statement before and just kind of inserts a not in there at the last bit to make it a negation. And again, opposite truth value. So a conjunction is when you join two statements with the word and. And then a compound statement is basically kind of like a conjunction. It's a statement made up of two other statements. So a conjunction is using the word and, so and is the conjunction, and then a compound statement is the entire thing you get after using that conjunction. So for example, let's have two statements here. A number multiplied by 2 is even, and a number multiplied by 2 is not prime. And this is assuming we're not using 1 or 0 as the number. So a number, not 1 or 0, multiplied by 2 is even, and a number multiplied by 2 is not prime. A compound statement, usually in math terms, is written like this with this little caret symbol here. So this would mean P and Q. So that little caret symbol means the word and. So and in math speak is that little caret symbol. So P and Q, which means a number multiplied by 2 is even, and a number multiplied by 2 is not prime. So this would be my conjunction, or my compound statement. So this right here is the conjunction, and the entire thing is a compound statement. And a conjunction is only true if both of the statements are true. So for instance, a number multiplied by 2 is even. Well, that's true. If we take a number and times it by 2, it's going to be an even number. And a number multiplied by 2 is not prime. And that would also be a true statement, I believe. At least that I can't think of a number off the top of my head where if you multiply it by 2, it's prime. So yeah, so this would be a true compound statement because both its pieces are true. So this first part's true, this second part's true, therefore the entire compound statement is true. If you can think of a counterexample for one of these, let me know and I'll change it. But I believe that that's correct there. And hopefully there's not a number escaping my thought. So let's try a few more here. So use the following statements to write down a compound statement for each conjunction and then find the truth value. So we want the compound statement for P and Q. So P and Q, let's do 1A right here. 1A. I'm going to actually type this out here. So P and Q. So P says the figure is a triangle. So that would be the figure is a triangle. And Q would be the figure has two congruent sides. So and the figure has two congruent sides. So this would be my compound statement. Now it's referencing a figure here that's obviously not in this image here, which I probably forgot to put on. So let me draw just a figure here. We'll call this 30. We'll call this 70. We'll call this 80. And we'll mark it as boom, boom, and boom. So that would be the figure. Let's take this as the figure that we're referring to here. So the figure is a triangle. That's true. This figure is a triangle. It has three sides. So the first part there is true. The figure is a triangle. And the figure has two congruent sides. Well, in this case, each side is marked with a different number of dash marks. So this side has a different length than this side, which has a different length than this side. So in this case, that part here would be false. It does not have two congruent sides. So this compound statement has to be itself false. And yet, why is it false? Well, because one of the pieces that makes it up is a false statement. So again, if one of the pieces is false, then the compound statement itself in its entirety is also false. So let's try the next one here. Now, sometimes when they say not P and not R, they'll write it like this. So they'll write not P and not R. So this little squiggly or tilde means not. So that's the negation symbol. So this is not P and not R. So how would that be written in English form here? So not P, well, if P is the figure is a triangle, not P would be the figure is not a triangle, and not R. So R says the figure has three acute angles, so not R will be the figure does not have three acute angles. And that would be the compound statement. So not P, the figure is not a triangle, and not R, the figure does not have three acute angles. So we need to figure out, okay, what's the truth value of this? So what's the truth value of not P? Well, if P is a true statement, that means not P has to be a false statement. Because remember, the negation of a statement has to have the opposite truth value. So if P is true, that means not P has to be false. So this first part here would be a false statement, which means right away that the entire thing is false. So the entire thing is false because the first part of it's false anyway. So I really don't care about what the truth value of the second piece is, because if the first piece is false, then the entire thing is going to be false. But just for completeness sake, R here, the figure has three acute angles. Well, it does. Each of these angles is acute. It does have three acute angles. So that's true, which means that not R would have to be false. So in this case, it's doubly false. The first part is false and the second part is false. So the entire thing is false. Even if just one of them was false, the entire thing would still be false, but this is even more false than that, I guess you could say. So that's how you go about using compound statements. Again, you pick the statements that they give you. If there's a not in there, make sure you throw, or a negation there, make sure you throw a not in the statement, but you simply just write them with the word and between them. And then you just figure out the truth value by making sure that both pieces are true. That's why it's helpful to sometimes go through and find the truth value of each statement individually first. And then when you make your compound after that, you can figure out the truth value pretty easily by just seeing if any one of the pieces is false. Again, remember that this little caret symbol, this upside down V, is the word and in math lingo there. That means and then the squiggly, the tilde, means not. So those are some two new symbols that you want to make sure you start getting comfortable with. So a disjunction is basically the word or. So and is a conjunction. A disjunction is the word or, and it's represented by the normal V symbol. There's not really a special word for that, I don't think, so we'll just call it the V symbol. So it's a little bit different than the word and, although it kind of serves the same purpose rather. It still is used to connect two statements, but the main difference is when it's true. So let's take two statements here. Alex plays soccer and Alex plays volleyball. So the disjunction would be Alex plays soccer or volleyball. Or you could say Alex plays soccer or Alex plays volleyball if you want to write them both out completely. But this would be the statement P or Q. So this would be the disjunction of these two statements there. It'd still be a compound statement. It's just a disjunction compound statement rather than a conjunction compound statement. Now, the main difference between a disjunction and conjunction, other than using the word or, is that a disjunction is true if at least one of them is true. So all a disjunction needs to be true is for one of the pieces to be true. If just one of them is true, then the entire statement is true, unlike a conjunction where they both have to be. So cardinals have wings. We're talking about the bird here. Cardinals have wings and tigers have gills. Well, cardinals have wings. That's a true statement. Tigers have gills. That's a false statement, at least last I checked. So the disjunction would be cardinals have wings or tigers have gills, and that would be a true statement because the first part of it is true, the second part of it's false. But because it's a disjunction using the word or, all I need is at least one piece to be true in order for the entire thing to be true. If I said cardinals have wings and tigers have gills, then this would be a false statement because a conjunction needs both pieces to be true. So disjunction is a little bit less strict than a conjunction because, like I said, all it requires is one true piece to it. So let's see if we can't write some here. So we have these statements. January is a fall month, January only has 30 days, and January 1st is the first day of a new year. Let's figure out the truth value of each of these individually first. So the truth value for P, January is a fall month. That's false, I believe. January is more so in the winter, again, right after December. Uh, January only has 30 days. I believe, last I checked, that's going to be false as well. January has 31 days. Um, January 1st is the first day of a new year. Now, again, depending on where you're at, January 1st might not be the day you mark the new year, quote unquote, but for most people in most countries, this is a true statement. So January 1st is usually the first day of a new year. So I just say a true statement. And then we should probably get the truth values of each of the negations too, because I see down here that we're going to have to do some negations. So let's get the truth value of the negations then. So that means that if P is false, that means not P has to be true. If Q is false, that means not Q has to be true. And if R is true, that means not R has to be false. So that way we're all set when we make these and write these out here that we automatically know whether the truth value is true or false. So let's do 2A first. So it says R or P. Okay, so 2A. So R is January 1st, the first day of a new year. So January 1st is the first day of a new year. Then so or P. So January is a fall month. So we need to figure out, is this true or false? Well, we know that R is true, and we know that P is false, because again, these are not negations, these are the original statements. So if R is true and P is false, that means the disjunction is going to be true. Because all a disjunction needs to be true is to have one true piece in it for the entire thing to be considered true, which is what the R does. Let's do 2B here. So 2B is Q, which is January has only 30 days. Or again, upside down, or sorry, the normal V here, the V shape is an or statement. Or not R. I mean, there's down here, there's that negation symbol in there. So not R. So R is January is the first day of a new year. So not R would be January 1st is not the first day of a new year. So again, not R means we have to put that negation in there. So is this going to be true? Well, Q we know is false. Again, normal Q statement is a false statement. January only has 30 days. It's false. And then not R we know is going to be false as well because January 1st is the first day of a new year. So the not version is going to be a false statement. That means the entire thing here is going to be false. Because both pieces are false, therefore the entire thing has to be false. There's no truth value in there or no true statement in there to hold it together. And lastly, we do 2C here. So P or not Q. So P is January is a fall month, or and then not Q. So Q says January only has 30 days, so not Q would be January does not have only 30 days. Notice how I didn't say January has 31 days, because the negation doesn't mean you change it willy-nilly. Negation means you actually have to use that word not. So you have to use that word not or something like it in there. You can't just change it to January has 31 days, because yes, we know that months, except for February, months usually have 30 to 31 days, but the way we'd say it in math terms is we'd have to use the word not to get the entire negation in there. So again, just be careful with negations that you don't change it to what you believe would be the true version. Just make sure you throw that not in there and let it be. So is this true? Well, P is a false statement, normal P. Not Q. So Q is a false statement, so not Q we said is a true statement. So that means the entire thing is going to be true because there's one true statement in there to hold it together and give us a truth value of true. So disjunction, just use the word or, and again, you're looking for one true statement in the entire thing in order for the full disjunction to be true. All right, so now we get to kind of the big picture here. So conditional statements. Conditional statements are statements that are not quite compound. So I guess you could consider them sometimes compound. But the main thing for conditionals is that they're statements that can be written in if-then form. And this is the form that we're going to write and talk about a lot of stuff in geometry, is this if-then form. So if the hypothesis, which we usually call P, then the conclusion, which we usually call Q, which is why you keep saying that P and Q float around it. These are just the typical variables to use to represent the hypothesis and conclusion. It's a little bit different than what you might think of in science, where you have a hypothesis that you test and then come to a conclusion. In math, it works like this. So if it is snowing, then it is cold outside. So this is a conditional statement. It's saying that if it's snowing, so this is the condition, I guess you could say. If the condition of snowing is met, then it's cool outside would be the conclusion that we assume is going to be reached. So if it's snowing, so it is snowing would be my P, then it is cold outside. So it is cold outside would be my Q. So if this is true, then I'm concluding that this has to be true. So it's kind of a version of a compound statement. And you can change a lot of the statements into conditionals. Like, for example, you will lose points on your test for questions you don't answer. That's not a conditional statement itself, but you can change it to be a conditional by just flipping it around a little bit. If you don't answer questions, then you will lose points. This is essentially the same thing, just written as a conditional. You don't answer questions would be the hypothesis P, then you will lose points is my conclusion Q. So we're going to go into figuring out, okay, how can we tell whether these are going to be true or false, and what are the conditions for it to be true or false? Because it is a statement, therefore it does have a truth value to it. So just to go over some math lingo here real quick, we've seen that a disjunction is V, which is the or. A conjunction is the upside down V, which is the word and. For a conditional or for a conditional statement, you use the arrow version. So P arrow Q means if P then Q. Or sometimes people say P implies Q, just a fancy way of saying it. But if you see that little arrow symbol, that means if this first statement, then the second statement. That's what it means to be a conditional. It's usually if then. So if the forecast calls for rain, then I will take an umbrella. That is a conditional statement or an if then statement. The hypothesis, again, is usually represented by the variable P. The conclusion is usually represented by the variable Q. Sometimes we use M and N as well, from what I've seen. But again, you can technically replace P and Q with anything because they are just variables. They're there to represent the hypothesis and conclusion. So if you want to put it as H and C, if that's going to work better for you, feel free. It's just a variable. So let's see if we can't change these into conditional statements. So 3A and 3B. So 3A says 4 quarters can be exchanged for a $1 bill. So let's see if we can't change this to a conditional. So we can say if you have 4 quarters, comma, then you can exchange them for a $1 bill. That would be a conditional statement. If, so the hypothesis is you have 4 quarters, then the conclusion is you can exchange them for a $1 bill. So that'd be how you would change that into a conditional. You just take it, split it into two statements. So 4 quarters is your first, exchange for a $1 bill is your second, and just put it in if then. So for 3b, the sum of two measures, the sum of the measures of two supplementary angles is 180. So let's break this down here. The sum of the measures of two supplementary angles is 180. So we have sum of the measures is 180. So this one's kind of split. Sum of the measures is 180. And then our second statement is actually going to be this middle one here, which is two supplementary angles. So the way I would write this, again, this one's a little bit trickier to break down. I would say if two angles, let me do it in the way they wrote it here. If the sum of the measures of two angles is 180, then they are supplementary. So I have the first hypothesis here. If the sum of the measures of two angles is 180, then my conclusion is they are supplementary. So this one required a little bit more movement than the first one, which can be kind of split down the middle. This one required you to kind of take the idea as a whole and see that you had two things here. You have angles adding up to 180, and then you have angles being classified as supplementary. So those were your two concepts, and you can put them in an if-then form there. And you can reverse these, by the way. So for 3b, I could say if two angles are supplementary, then the sum of the measures is 180. Or for 3a, I could say you can exchange for a $1 bill if you have, or sorry, if you exchange coins for a $1 bill, then you had 4/4. So you can change it around, something like that. So you can have a little bit of leniency with how you organize this stuff here, as long as, again, the end statement sort of makes sense. So when are conditionals true? So to prove a conditional true, it has to be true for every single case that it's stating. So if a figure is a triangle, then all its angles add to 180. This is a conditional, and it does happen to be true. So for every single possible triangle I can think of drawing or making or writing or imagining, every possible triangle. Now again, this doesn't assume a Euclidean space, as we said in the very, very, very first chapter of this entire course here. This is all assuming Euclidean space here. No matter what type of triangle I draw, the angles will always add to 180. This is true for every single case, and it can be proven true for every single case, which is a little bit more detailed than I want to get into in this video, but we do prove it later on. But this is a true proven statement. To prove it false, all you need to do is provide one counterexample for a conditional statement. So this conditional statement here would be false. If a figure is a triangle, then it has no right angles. So the way I would prove this false is just draw a right triangle. There. It's a triangle. It does have a right angle. Therefore, this conditional has been proven false. So if you want to provide a counterexample, you want the hypothesis to be true. So you want P to be true in your example, and you want the Q to be proven false. So you're looking for an example where P is true and Q is false, like this one. In this case, P is true. It is a triangle. Q is false. It does have a right angle. So therefore, the conditional has been proven false by this counterexample. So for example, I couldn't do this. I couldn't do something like this. Maybe say this is 110. This is 110. This is 40, and this is 40. This wouldn't be a counterexample because is a triangle, so it serves to prove that P is correct. It is a triangle. Then it has no right angles. Well, this does not have any right angles, so it can't be used as a counterexample because it follows the hypothesis. It's a true statement. So this I can't use as a counterexample because it's a triangle with no right angles. So P is true and Q is true. I'm looking for example where P is true and Q is false. Also, I couldn't do this. So here's a rectangle. Hey, it has right angles. Well, okay, if the figure is a triangle, this is not a triangle. Therefore, it cannot be used as a counterexample because the first part of it isn't true. So you're looking for a counterexample where the P part is true and the Q part is false. The first part the if part has to be true, the then part has to be false in order to be an accurate counterexample. Now, one of the weirder things with this structure of logic is that if the conditions of the hypothesis can't be met, then the statement is assumed to be true. So for example, if pigs can fly, so pigs can fly is my hypothesis P, then 2 plus 2 equals 8. That's my conclusion Q. This would essentially be assumed to be true because we cannot construct the means to make it false. We can't construct a situation where pigs are flying and 2 plus 2 is not equal to 8. Because if I just say, well, I know 2 plus 2 is 4, the response to that would be, well, your hypothesis isn't met yet. Pigs aren't flying. So of course 2 plus 2 is 4, because pigs aren't flying yet. Once pigs start to fly, then 2 plus 2 would equal 8, would be what this statement is saying. Now, is that true? We can probably safely assume it's not going to be. If pigs suddenly start sprouting wings and flying, we can probably safely assume that 2 plus 2 is still going to be 4. But given the structure of this logical system here, we'd have to just say that until proven otherwise, this is a true statement. So think of as statements as innocent until proven guilty. So if I say that if Earth's gravity suddenly stops and the world stops spinning, then 5 plus 1 is going to be 10. That would essentially be a true statement because you can't disprove it yet. So you have to be able to provide a counterexample in order to assert that a statement or a claim is false. Now, obviously, this is a useless statement because it's not going to help us at all, but this is some quirky little aspect to the system of logic here. It doesn't really come up that much, so if that doesn't quite jive with you, you don't have to worry about that. But I just figured I'd throw that in there because it's kind of a quirky little wrench in the cog of things. So therefore, again, I know this video's long here, so I told you there's going to be a lot of information. If you want to stop and take a break, go ahead, you can pause. There are four types of forms that we have for a conditional. So there's the normal conditional statement, if P then Q. Then we have converse, inverse, and contrapositive. So the converse is basically when you flip the statement. So converse means you take your conclusion, make it your hypothesis, take your hypothesis and make it your conclusion. So you switch P and Q. So if the original statement was, if A is 35 degrees, then A is acute, the converse would be flipping them. If A is acute, then A is 35 degrees. So the converse is just the flipped form of the original. The inverse is the not form of the original. So the inverse does not swap them. The inverse simply takes it and says not P and not Q. So if A is 35 degrees, then A is acute. So the inverse would be if A is not 35 degrees, then A is not acute. So P and Q are still in their respective spots, but they're just negated. They have the not, they have the nots thrown in there. And the contrapositive is both. So think of the contrapositive as the converse. So converse plus inverse. So the contrapositive is the converse plus the inverse. You flip them and you negate them. So this would be if A is not acute, then A is not 35. So I swapped my hypothesis and conclusion, and I swapped my hypothesis and conclusion, and I negated them in my statement. Now, these do not all follow the same pattern. So if this is true, so if A is 35, then A is acute. That's a true statement because acute angles are angles that are less than 90. So if A is 35, then A is acute. The converse, if A is acute, then A is 35. This is a false statement. So the converse and the original do not always have to be both true and both false. They can disagree. Sometimes these are both true. Sometimes these are both false. Sometimes one is true and one is false. We don't know. There's no relation between them essentially. Because in this case, my counterexample for this would simply be something like this. So this is an acute angle, but it is not 35. So that would disprove this converse right here. If A is acute, which this is, then A is 35. It's not. I'll call this angle A here, just to be clear about it. The inverse also, again, doesn't have any relation to the original statement. So if A is not 35, then A is not acute. Well, that's going to be false, because once again, I can use the same counterexample. Here, A is not 35, so that meets the hypothesis. Then A is not acute. Well, it is acute, because it's less than 90. So therefore, that provides a counterexample, and this statement is false. And then the contrapositive, if A is not acute, then A is not 35. So if A is not an acute angle, that means that A is going to be more than 90 or equal to 90, because acute angles are all angles that are less than 90. So if A is not acute, that means it's 90 degrees or more, then A is not 35. Well, that's actually going to be true, because if you're going to be 90 or more degrees, then you obviously can't be 35 degrees. So in this case, that statement is actually a true statement. There is no counterexample for that. So the logical link here is that the original and the contrapositive, these two are always going to share the same truth value. So if the original is true, the contrapositive is true. If the original is false, the contrapositive is false. And then the converse and the inverse, these are going to share the same truth value. So if the converse is false, the inverse is false. If the converse is true, the inverse is true. So converse and inverse are linked, original and contrapositive are linked. And we'll see that coming up here in a few examples. So statements that have the same truth value are said to be logically equivalent. So again, if statements are both true or both false, it's kind of like being equal. It's kind of like saying 1 equals 1 or 2 equals 2. So just when we talk about statements being equal, that means they both are either true or they both are either false. So let's go ahead and write this down. So conditional means the original statement. So think of conditional and original as the same thing. So two angles have the same measure are congruent. So two angles that have the same measure are congruent. There's some water there. So we want to write this as a conditional statement. So two angles that have the same measure are congruent. So we can say if two angles have the same measure, then they are congruent. So again, we have our first statement, two angles that have the same measure, and then our second statement is they are congruent. Now, is that a true or false statement? Well, this would be true. because that's what it means to be congruent. It means you have the same measure. So if two angles have the same measure, by definition, they are congruent. That's a true statement. Let's see what the converse would be. So the converse would be the flip form. So again, this is, I'll even write down here. So two angles have the same measure. That's my P. Then they are congruent. That's my Q. The converse is the flipped form of this. So the converse says swap P and Q. So if two angles are congruent, then they have the same measure. If two angles are congruent, then they have the same measures. So now my Q is over here. Two angles are congruent. That's my Q from my original. So boom, just got swapped. And then over here is my P from the original. So again, boom, just got swapped. So just swapped P and Q. And this would also be a true statement. If two angles are congruent, they have the same measure, which again, by definition, in order to be congruent, you have to have the same measure. So that's what this is saying here. So this would also be a true statement. So again, sometimes both the conditional and the converse are true. They don't always have to be opposites. So the inverse is not P and not Q. So the inverse is negate the first and negate the second. So if two if two angles do not have the same measure, then they are not congruent. So negate P and negate Q. If two angles do not have the same measure, then they are not congruent. And this would also be a true statement, because as we said before, the converse and the inverse are always going to have the same truth value. And the conditional and the converse are always going to have the same truth value. So we know that the conditional and the contrapositive, not the converse. The conditional and the contrapositive are always going to have the same truth value. So we know that the contrapositive is automatically going to be true because the conditional was true, without even writing it down. But if we write down the contrapositive is flip and negate. Or you can think about it as the inverse of the converse. So the contrapositive is the inverse of the converse. So take your converse and then negate it. So converse says if two angles are congruent. So I'm going to start with if two angles are not congruent. Then they have the same measure. So then they do not have the same measure. So I negated my converse. I took my converse and I negated the first and the second statement. Or I guess you could also think about it as flipping your inverse. So think about it as the inverse being flipped. So you take your Q, you take your P, and you flip it that are on the inverse. And as we said here, this is going to be, this is going to be a true statement. Because again, if the conditional is true, the contrapositive also has to be true. I said angels there, should be angles, my bad. So let's try one that's a little bit more mathy in focus here. Let me shorten this up a little bit so I can get all of it on screen. So a number that is divisible by 4 is divisible by 2. So again, let's do our conditional here. So a number that is divisible by 4 is divisible by 2. So that would be if a number is divisible by 4, then it is divisible by 2. So this, this would be my statement. If a number is divisible by 4, then it is divisible by 2. And that would be a true statement. If you can divide it by 4, then you can divide it by 2. There is no counterexample for that. If you can think of one, please let me know. But every number that can be divided by 4 can also be divided by 2. So what's the converse here? So again, let me write down my P and my Q. So a number is divisible by 4, that's my P. Then it is divisible by 2, that's my Q. So what's my converse? The converse is the flipped form of this. So if a number is divisible by 2, then it is divisible by 4. So if a number is divisible by 2, then it is divisible by 4. That would actually be a false statement. So I need to provide a counterexample if I'm going to say it's false. And my counterexample would simply be the number 6. So 6 can be divided by 2. So 6 divided by 2 is 3. So it's divisible by 2. but 6 cannot be divided evenly by 4. So 6 divided by 4 is some decimal number. So point something, 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 something. I think it's 1 point something, something, something. But since it's not a whole number, then it's not divisible by 4. So that would be my counterexample is the number 6. So, whoops, need to make sure that stays there. Let me lock that in place real quick. Lock. So that would be my counterexample to prove that it's false. I could also have chosen stuff like 10. I could have chosen stuff like 30. So there's a whole bunch of other counterexamples you have too, but that's just one of them because all you need is one to prove that's false. Now, because of this, we also know that the inverse is going to be false too, right? Because the converse and the inverse have the same truth value. So we know the inverse is going to be false right off the bat. But let's go ahead and write it down first just to be sure. So the inverse is the negation of the conditional. So if a number is divisible by 4, so the inverse would be if a number is not divisible by 4, then it is divisible by 2, so then it is not divisible by 2. So a negation the first. So if it's not divisible by 4, then it's not divisible by 2. And I can do a counterexample like for that. And again, same thing, 6. So 6 cannot be divisible by 4. So 6 meets the conditional. It's not divisible by 4, but it is divisible by 2. So it proves the opposite of the conclusion. So again, 6 works because it follows the first part of the statement, but breaks the second part. Same thing up here. It follows the first part of the statement. 6 is divisible by 2. That meets the hypothesis. The hypothesis is true, but the conclusion is false. So same here. Hypothesis is true, but conclusion is false. That's what makes it a counterexample. So this is going to be a false statement. And lastly, the contrapositive. Again, we know it's true because the conditional is true, and the contrapositive and conditional are always linked up. But the contrapositive, remember, is the flipped form of the inverse or the negation form of the converse. Let's negate the converse because that usually is easier for me. So negate the converse. So converse is here, remember. Converse is the second one. So if a number is not divisible by 2, then it is not divisible by 4. And again, we said that's going to be a true statement because there is no counterexample for that because it's true. Again, if the conditional is true, contrapositive is true. So we know that's going to be that heading into it. All right, so last little bit here, I promise. Again, there's a few more to go. As I said, long lesson, so again, take a break if you need to. Biconditionals. So biconditionals are statements using if and only if, and they are compound statements. And they are a form of conjunction, so they follow the and rule. So let's take a biconditional here. The biconditional actually is made up of two specific statements, a conditional and its converse. So if you take the conditional and its flipped form, remember converse is flipped, so take the conditional and its flipped form and you put them together with the word and, then you get a biconditional. So let's take this here. If two angles are complementary, then they add to 90, which is true, by the way. If two angles are complementary, then they add to 90. That's the definition. The flipped form then would be if two angles add to 90, then they are complementary. So you just flip the two statements. So conditional and converse here. So the biconditional would be taking both of these and putting them together. If two angles are complementary, then they add to 90. That's my conditional. And if two angles add to 90, then they are complementary. That's my converse. So we usually don't write biconditionals like this because it's a mouthful. So we usually write it using this if and only if form. So if and only if means that you're going to take one statement, usually conditional, and just swap out the then for if and only if. So two angles are complementary, not then, but two angles are complementary if and only if they add to 90. So these mean the same thing. So putting them together with the word and using if and only if is the same concept. It's just that this is a lot easier to write, so we usually write it in this form. And all this is your conditional statement, but you drop the if and you take out the then and you replace it with if and only if. Now this doesn't look like much, but when you see this if and only if, that means that this statement is true forwards and backwards. So if two angles are complementary, then they add to 90, and if they add to 90, then they are complementary. So when you hear the word if and only if, that's what it's implying. So it's a little bit of a stronger implication than just your normal if-then type statement. So let's go changing one here for a second. So to change it to a biconditional, as I said, you drop the if, and then you replace the then with if and only if. So let's take this one here. If you drive too fast, then you will crash your car. So you will drop the if and replace the then with if and only if. So you drive too fast, if and only if you crash your car. So what this means here, this implies that if P, then Q, and if Q, then P. This would be it in kind of math lingo there. If P, then Q, and if Q, then P. So if you drive too fast, you will crash your car, and you will crash your car if you drive too fast. That's what this is implying here. Now let's talk about when the biconditionals are true, because it sounds like they sound easier than they are, to be honest. So a biconditional is true if and only if the conditional and the converse, or sorry, the converse and the inverse of the original is true. So again, let's just take this here. If an animal is a snake, then it is a reptile. That's true. So the converse would be if an animal is a reptile, then it is a snake. Well, that's false. There are reptiles that are not snakes. The lizards, for instance, are reptiles that are not snakes. So the original statement is true. The converse is false. So the biconditional would be an animal is a snake if and only if it's a reptile. Well, that would be a false statement. Why? Well, because it is a conjunction. And this shouldn't say inverse, by the way. I miswrote this here. Let me change this right now. This should be if a biconditional is true only if both the original and converse of the original is true. So it shouldn't, the inverse has nothing to do with the biconditional. That's my bad there. So a biconditional is only true if the original and the converse are both true. So this is an example where it's false because the original statement is true. The converse is false. Therefore, the biconditional that they make is also going to be false. Because you can think of a counterexample here. An animal is a snake if and only if it's a reptile. Again, the counterexample would be lizards. A lizard is a reptile, but it is not a snake. So it works forwards. Going this way, it works. If the hypothesis is true, the conclusion is true. That's okay. But it fails going backwards. If the conclusion is true, the hypothesis is not always true. So it does not work that way. So as a biconditional, it fails. As a normal, everyday, original conditional statement, it's true. But as a biconditional, it fails because it does not go backwards. So a biconditional has to be true forwards and backwards. So let's try for you here. So if two angles are congruent if and only if their measures are equal. So we need to check two things. In order for this to be true, the original would be, if we kind of reverse this, the original would be if two angles are congruent, then their measures are equal. That's the original version. And the converse would be the flip of that. So if two angles have the same measure, I'm typing fast, so I'm thinking measure, then they are congruent. So if both of these are true, then the biconditional is true. So let's go ahead and read them here. If two angles are congruent, then their measures are equal. Well, that's true because that's the definition of congruency. If two angles have the same measure, then they are congruent. Well, that's true because that's what it means to be congruent, that you have the same measure. So because both these are true, that means the biconditional itself is going to be true. Okay. So this is true both forwards and backwards. The original statement it's derived from is true, and the converse statement of that original is also true. A point is a midpoint if and only if it's between 2 points. So it needs to be true forwards. So forwards would be if a point is a midpoint, then it is between 2 points. And that is true. If a point is a midpoint, it has to be between 2 points. So if you have point A here and point B here, the midpoint has to be somewhere between them. You can't have the midpoint over here, for instance, because that's not in the middle of A and B. So going backwards then, backwards means you read this in reverse. So if a point is between 2 points, then it is a midpoint. So backwards is actually false, because what I could do here is, let's say here's A and B. Let's say I put point C right there. So point C is between 2 points, but it is definitely not a midpoint. Point C is much closer to B than it is to A. So C fits the conclusion, it's between 2 points, but it does not fit the hypothesis where it's a midpoint. So this biconditional itself would be false. This would be a false biconditional because this is my counterexample. Again, it works forwards. A point is a midpoint if it's between 2 points. Or sorry, if a point is a midpoint, then it's between 2 points. That works. But the backwards version of if conclusion, then hypothesis. So if a point is between 2 points, then it's a midpoint. That doesn't work because of this counterexample right here. So again, it has to work both forwards and backwards. So last one here. You have homework if and only if you are in math class. Let's go ahead and go forwards. So if you have homework, then you are in math class. So again, depends on who your teacher is, I guess. But if you have homework, then you are in math class. I believe that would be a false statement because you can probably have homework and not be in math class. Like you can be in English class or you can be in science class and have homework. So that would be a false statement. If you have homework, then you're in math class. So I can think of a counterexample where you have homework, science class, but you are not in math class, which means that you're in science class, obviously. So that would be a false statement going forward. So this biconditional automatically is false because it does not work forwards. Let's see if it works backwards, though. If you are in math class, then you have homework. And again, depending on your teacher, if you have me, that's probably true. If you are in math class, you probably do have homework. That's probably a true, probably a true statement most of the time. But again, because the forwards version is false, the entire biconditional is going to be a false statement. So again, biconditionals are trickier than they might first look because most people check the forwards version. Most people check if this, then this. But they fail to remember to check the backwards version. So if you see this word if and only if, which also, by the way, if and only if sometimes is abbreviated as IFF. So you see this IFF, it's not me misspelling something. That's actually how you say if and only if in sort of math shorthand is IFF. But again, it's just a tidbit there. So most people check the forwards version, but they don't check the backwards version. So always check both ways if you have a biconditional. If you just have a conditional statement, an if-then statement, you only need to check one way. But if it's biconditional, again, the word bi being two, you need to check both ways of the statement and make sure it works in both directions. And yep, I believe that's the last one. So as I said, longer video, I know. Thank you for sticking with me if you stuck around. Again, don't be afraid to recap this or go over certain points in this video if they were a little bit confusing. And as always, let me know if you have any questions. I'll be glad to help you out as much as I can. So hopefully this helped you out. Thank you for sticking with me. Have a good day.